Hi everybody. In this video today, we're going to look at section 2.2. This is the last section that's on your first exam. And it ties together stuff that we've seen so far and also sets us up for what we're going to be doing for a lot of the rest of the course. It's a very, very important section. And I'm going to start with slide 2 here. So this is the main definition that we use for the first, two more chapters, really. All of chapter 2 and chapter 3 are based on this definition. So the derivative of a function is a function that takes every value x in the domain and returns the slope of the tangent line. So you input a function and the derivative tells you the slope of the tangent line at that point. So it's a very powerful tool. So you could do it just with a graph, right? If you have a graph, you can estimate the slope of the tangent line. Or if you're given the derivative, it tells you the slope of the tangent line just from a graph. So it works with equations or graphs. And we're actually going to see both type of examples in this lecture today. There's only 4 examples, but they're all pretty large, as you'll see. So let's jump in and see how to use this derivative idea to draw the sketch of a derivative of a function. So here's our function. So we want to draw a graph that represents the slope of the tangent line of every point on this graph. So that might sound super duper tough. So we're going to be real systematic about it. So this is the way you should approach these problems on the homework, because on a test, if I ask a question about this, this is probably the way you're going to want to do it that gives you the best chance of getting the right answer. So what points do we know the slope just looking at this graph? Well, I can only see 4 points where I know what the slope is. Here, 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 and here. The slope at all 4 of those points is horizontal. So the tangent line is horizontal. That means the slope is 0. So I would plot those 4 points first. So you take the slope that you get from the original function and you plot those on the x-axis. Next, you fill in the points in between those points. So here, for example, at -2, the slope here is about 5. So you plot the point 2, 5. I'm sorry, -2, 5 on the derivative graph. And here at 1, it looks like the slope is about -1. So you plot 1, -1 on the derivative graph. So you don't need a lot of points to do this. You only need to find a few of them. Just sort of take where the slope is 0, find a couple points in between, and it just allows you to get sort of a picture of what the derivative graph will look like. And now we have all these points down here, right? And so we can just connect them together. So you just go up and through, come down, go back up, back down, and back up. And you end up with this graph. So here is the finished picture of the derivative. Drawing these by hand does take some practice. Make sure you guys are taking this stuff seriously. Even though the homework is multiple choice, so it might seem kind of easy, don't be fooled, right? You have to demonstrate proficiency with the concept on an exam. Not going to be too many multiple choice on the exam. And then you can check your answer by comparing it to the original function, just to make sure everything lines up. So pick a point, estimate the slope. Does it look like that's where the derivative is? Right? So, I don't know, here at 0, right? What does the slope look like here? Well, if I draw a line from 0 up to here, it's about 2.5. So it's a negative slope, so -2.5. And if you look over on the derivative, it passes through the point 0 around -2.5. And that's it. So the idea is that you just want to take a function and turn the function into a different function that tells us the slope of the tangent line. That's it. That's all we're doing with derivatives. Okay, in the next example, we are given two equations. And with these formulas, I'm going to plug these into the definition of the derivative. And we're just going to simplify with algebra. That's the idea. So let's look at part A here. So the function is square root of 1 minus x. So f of x plus h is just square root of 1 minus parentheses x plus h. Minus f of x, well, there's f of x over h. So this is what we're trying to simplify, this limit. And you might think, well, can't I just plug in 0? Well, what happens when you plug in 0? You get a 0 in a denominator, and it turns out you get a 0 in the numerator. That will always happen when you try to plug these in. That means we need to simplify first. And so we've seen problems like this one before. You're going to want to distribute this negative. That's this like gray part here is the negative being distributed. Then you take this expression here and you say, how do I get that h out of the denominator? To get an h out of a denominator, I need to get this h by itself. And then those h's will cancel. So I need to multiply this whole thing by the conjugate. So you just take whatever this looks like, flip the sign. This will always be a minus because of the formula. So you're just going to take this first term and then change this to a plus, and then the second term. And then you write that expression over itself. That's called the conjugate. When you do that multiplication, everything will fall out, the h's will cancel, and you'll be able to plug in 0. So because we're multiplying by the conjugate, we're going to FOIL this numerator, right? This is a difference of squares. So it's that times that is that. That times that is that. And the two middle terms cancel out. The denominator we don't mess with. So don't distribute this h in the denominator because we're trying to get the h to cancel. So leave the h alone. You never have to distribute denominators early on in the class when we're working on this stuff. Now that we foiled the denominator, we can actually simplify. Sorry, we foiled the numerator. We can actually simplify the numerator. So 1 minus 1 goes away, that's 0. Negative x minus negative x, that goes away, that's 0. We're just left with negative h, which goes here. And our numerator is simplified. Again, we don't mess with the denominator at all. Now we want to cancel that h. So negative h and h cancels. We're left with negative 1 in the numerator. Now, as soon as you cancel h, you're ready to plug 0 in. So plug 0 in here for h. And simplify it. And that's what you get. Negative 1 over 2 times square root of 1 minus x. So this is pretty cool. You start with this, and you end up with this. The domains stay the same, right? They kind of have to, or they stay very similar. They don't change. The domain won't change too much. So this function is only defined for numbers 1 or less. This is only defined for numbers less than 1, right? So this is a pretty neat tool. You can imagine in science how important this would be, right? And this was, well, we're going to learn a little bit of the history in this slideshow. I'm not going to go over it. I'll let you guys read it. But this was developed in the mid-1660s by two different people at the same time. All right, let's do another one. So back-to-back examples. Here we have a different kind of function. So here I called it k of t. I just want you to get used to seeing different letters. It doesn't always have to be f of x. It could be f of t. It could be k of x. Doesn't matter. This is a rational function. Notice t is not allowed to be negative 2 because that's division by 0. That means we would expect this to show up in the derivative, and it turns out it does. Because 2 is not part of the original, sorry, negative 2 is not part of the original function, so it can't be part of the derivative. So there's the derivative formula. So we're going to plug everything in, but before I do it, I'm going to show you a way to save yourself some algebra headaches. Okay, so what I did here is I rewrote this limit to make the algebra easier. If you're good at algebra, you don't have to do this step. You can just work straight down the other side. If you're a little nervous about the algebra, you're going to want to do what I do here, which is break everything into smaller bits in order to do the calculations. So I'm going to compute and simplify only the inside of this. I'm going to ignore the limit. I'm going to ignore the 1 over h for now. I just want to know, how does this inside part simplify? Let's see what happens. So you plug in what you know, right? So k of t plus h is this with t plus h plugged in here. Minus k of t, so that's our original function. Now I have to simplify this thing. So I'm going to distribute this negative, and I have to get a common denominator. So I distribute this minus sign here, right? That's this. Right? So it's 1 minus t minus h. Then I have to get the common denominator. We have 2 plus t plus h and 2 plus t. They don't have any common factors, so I have to multiply each one by the other factor. So we multiply this by 2 plus t over 2 plus t, multiply this by 2 plus t plus h over 2 plus t plus h. That's our common denominator. Next up, you just FOIL all the numerators. So that's what I did. Notice I didn't mess with this negative yet. I did not distribute this negative yet. Again, you want to make the algebra as painless as possible. It's okay. Oh, sorry, this negative. I didn't distribute this negative yet. This one stays. This one's from this. This negative here, I didn't distribute it yet. I left this all in parentheses. What you're going to see is it doesn't matter if you distribute it or not. Right? It's just as easy to work through, so you might as well just leave it there. So this whole thing right here, this k of t plus h minus k of t, turns into this ugly mess. And this happens a lot in a class like this. It's just a lot of algebra, right? We haven't even done any calculus yet, right? We haven't done any limits yet. This is all just algebra. Okay, so I FOILed all these numerators, right? So 1 times 2 is 2. Negative t times 2 is negative 2t. Minus h times 2 is minus 2h. And so on and so forth all the way across the top. I just FOILed all those numerators. Notice the denominator, you don't FOIL, right? Just always leave the denominators alone, okay? Trust me, it's extra work you don't need to do, and it's easier if you don't, right? It's easier if you don't FOIL them, the denominators. So we simplify that numerator. It turns out everything's going to cancel in this numerator. So 2 and the minus 2 here, those cancel. That's 0. Here we have a minus 2t and a minus 2t. That's 0. The only thing that doesn't cancel is this minus 2h and this minus h. So we have a minus 2h and a minus h. That becomes minus 3h. And our denominator stays exactly the same. So what I did is I simplified this expression inside this limit. I just got a simpler version of it, that's all. So I put everything back into the derivative formula. Here's my derivative formula. Now I plug in that simplified expression at the top of the slide, and I get this. Now we're ready to cancel the h, right? The whole point of doing this was so h would cancel. So those h's cancel. As soon as you cancel h, you're ready to plug in 0 with direct substitution, right? So here we have an h in the denominator. Just plug in 0. And after you simplify, you get negative 3 over 2 plus t squared. So again, pretty cool problem. Yes, it's a long problem. Yes, there's a lot of steps. That's calculus. Wait till you guys get to Calc 2. For those of you taking Calc 2, you'll kind of wish you had problems like this again. For those of you not taking Calc 2, you can take it for fun if you want. So it's worth looking at our original function again. Right, here's our original function. And then look at our derivative. Right? Negative 3 over 2 plus t squared. So that original denominator always sticks around. think about why that might happen, because we're going to learn a rule for that later on, and it helps make this make sense. So that's two more types of problems. I'm going to show you one further type of problem. And then you'll be able to basically do everything on the homework. Not so much for this section, okay? But also moving into the next section, section 2.3, that's not in this first exam. The stuff we learned today, you're going to use in future sections. So using the definition of the derivative, find the derivative of the parabola. So every parabola that points straight up or down has the formula ax squared plus bx plus c, right? It's where the quadratic formula comes from. So the quadratic formula tells us where the parabola intersects the x-axis. We want to know something a little bit different. We're going to find the derivative, and we're going to use that derivative to show that the vertex of a parabola has the coordinates listed at the bottom. So you may have learned in college algebra that the vertex of a parabola has that formula. And you said, well, where does that come from? Why does it happen? And it was probably some complicated geometric argument. We're going to show that it's an argument based on slopes. So let's jump right in. So our function is ax squared plus bx plus c. Now, I could plug this all into the derivative formula, but that, you can see right here, we have a FOIL. I'm going to do that side work again, so I don't have the annotations in this example, just to show you what it looks like kind of at full speed. So I'm going to compute the f of x plus h by itself first and simplify it. Let's see what happens. So f of x plus h, you plug x plus h in for all these x's. FOIL. Right, so from here to here, all I did was FOIL this. Distribute. Now, that is the distributed and FOILed version of this. Now I have my derivative formula. So where I see f of x plus h, I'm going to plug in this. Where I see f of x, I'm going to plug in this all over h. So you can see by doing a little side work, it saves you some writing, right? Now I'm ready to get stuff to cancel. So what should cancel in the numerator? Well, we need enough stuff to cancel, so this h goes away. So it turns out everything that doesn't have an h will go away. Here's ax squared minus ax squared. That ax squared is going to go away. Here's a bx minus bx. That's going to go away. Plus c minus c. All those things go away, and we're left with this expression. All these have an h in them, so factor out the h, and then cancel the h. Leaves you with this. And of course, once that h is out of the denominator, you can plug in 0, and you get this. So this version, circle your answers. Once you guys get the hang of this, the stuff we've been doing in Chapter 1 and then the first two sections of Chapter 2, you're going to be able to work through it pretty quickly. You're going to kind of learn how the patterns work, right? If you have an h in the denominator, maybe you want to leave it there. Maybe you want to pull it to the front as a 1 over h. That's up to you. If you can see that plugging in this f of x plus h is going to lead to a very long, chained out expression, maybe you want to compute that off to the side, save yourself some writing. Plus, if you make a mistake, now you only have to go back to here. You don't have to go back and do the whole problem again. It's very hard to find your mistakes if you chain everything together. If you just slop all the parts together and work through it, and you make a mistake, it's going to be tough to find it. And you're going to make mistakes, guys. It's what happens. So you got to learn how to deal with mistakes, how to correct them quickly, how to diagnose them. So that's why I got to be, really upfront and explain that you got to stay organized, right? And if you make a mistake, you got to find that mistake. All right, so that's part A. So that is the derivative. So every point on a parabola, the tangent line has this slope. Pretty cool. So how do we use this to show that the vertex of a parabola has the formula negative b over 2a? Well, you just use your horizontal tangents again, right? That's a very common way to solve problems in calculus. Every parabola has a horizontal tangent at its vertex. So we know the derivative is 0. So all we have to do is set 2ax plus b equal to 0 and solve. When you solve that expression for x, you get negative b over 2a. And the vertex is on the parabola. So its coordinates are xy is negative b over 2a for its x-coordinate, and then plug that value back into the expression. Right? So that's why it says f of negative b over 2a. And there you go. So that's a little bit of a preview looking ahead. This is the kind of stuff we're going to do in Chapter 3. Chapter 3 looks at graphical properties of derivatives. All right. So I'm going to let you guys read this. There's one more example, but I'm going to let you guys read. There's a lot of instructional material in here. I'm not going to go over all this. I'll let you guys read this. I do want to point out a couple things that I feel are important, though. Okay. So here's a mathematical definition called a differential operator and the process of differentiation. We are going to use probably every piece of notation on this slide at some point in this class. And the symbol, so the capital D, and then that d dx, this right here, these are called differential operators because they indicate a process of differentiation. This is one of the most overlooked things in calculus, okay? When you're doing a calculus problem, especially later on, you're going to have to do a bunch of algebra, and then you're going to do one step of calculus. You need to explain when that step of calculus took place, because if you don't, it's going to look really weird to anybody reading your work, because you're going to go, hey, what happened? Your function turned from blah, blah, blah into something else. So you have to understand that these things are called operators, which means you are saying, and now I take the derivative, and now I do the derivative thing. Okay, so watch out for that. Okay, so as we move through these sections, especially when we get to the end of Chapter 2 and Chapter 3, in the notes you'll see, I'll be very clear about when I'm taking a derivative. You'll see. All right, so it turns out that functions can be differentiable on intervals. But what I want to point out is the theorem at the bottom. So this is saying if f is differentiable at a, remember a is any point on the domain, then f is continuous. So this is saying that differentiability is a sufficient condition for continuity. That's really important. So if you know the derivative exists, that means the function is continuous at that point. We've already talked about why that would be true, right? You can't have a slope of a tangent line at a point if that point is not in the domain of the function. It wouldn't make sense. But it turns out we actually can prove that this is true, and this is very powerful, and we're going to use it a lot. So I don't know how much logic you guys know, but sometimes for these theorems I'll toss in the contrapositive just to show you how it works. For those of you who don't know, the contrapositive is taking the if-then statement in a proof, reversing the order, and putting the word not in both parts. So, if f is differentiable at a, then f is continuous at a. Switch those parts, throw in the word not. If f is not continuous at a, then it is not differentiable. It turns out if a statement is true, then its contrapositive is always true. Okay, so that's a foundational logic thing for those of you guys who have seen that. And if you haven't, we're going to do several proofs this semester. So being able to understand the contrapositive will help you prove theorems. So the proof is at the end. I'm going to do that proof at the very end. So remember, if it's differentiable, it's continuous. If it's not continuous, then it's not differentiable. So that's a pretty powerful statement. All right, I'll let you guys read all that. I want to get to here. This is right before our last example. And then I will talk about further study resources, and I'll talk about that proof. So it turns out that we can keep taking more and more derivatives, right? So if you have a position function, s of t, there are several higher derivatives that have special names. We've already seen position. We've seen velocity. Earlier in these slides, we saw accelerations, but acceleration is still new in this. Like, what is acceleration? It's still a new idea as of this slide set. And it turns out that the third derivative of position is called jerk. And the only time you've maybe ever realized that that exists might be on a roller coaster, because it's how fast your acceleration is changing. So velocity is how fast your position is changing, right? If your position is in meters, your velocity is in meters per second. So again, if we're doing meters per second, your acceleration is meters per second, right? So how fast is your velocity changing? So every second, your velocity is a different number. So your velocity is meters per second, which we sometimes just write as a notational convenience, meters per second squared. Your jerk is how fast your acceleration is changing. And this list goes on and on and on. There's a link to the Wikipedia article here. I was going to put it in the notes, but you guys wouldn't believe me what the names of the higher derivatives are unless you personally see it. So go ahead and click there. And believe me, it is true what you're about to read. So let's go ahead. If you want to check that out, pause the video and look it up. But we're going to go ahead and do example 4. So just imagine that this is some sort of roller coaster. And you're some sort of systems engineer, mechanical engineer, or physicist. And you need to know one of these is the position of a roller coaster and its first 3 derivatives. The velocity graph is there somewhere. The acceleration graph is there. And the jerk graph is there somewhere. We need to identify each curve. So if you're not sure how to do this problem, pause the video and think about it. Don't peek ahead. Because you have a couple of these on the homework, and I want you to really use logic to solve these problems, because that's what I recommend. So go ahead and pause it if you don't know how to do it, and then I will begin my instruction. But you should think about this. Calculus is not about filling in little boxes. Okay, it's about, hey, you know all that stuff that you learned algebra for? This is the stuff. All right, so this is a sort of logic puzzle. So curve A cannot be position, velocity, or acceleration. It can't. This is because it has 2 horizontal tangents, and none of the other graphs crosses the x-axis at those x values. So that means A must be S triple prime. Think about it. If A was the original function, then it would need to have a graph that crossed the x-axis twice at those numbers, just like we saw in example 1. But because that doesn't exist, that means the derivative of A does not appear on this graph anywhere. That means A must be the highest order derivative, so it's S triple prime. So that gives us A. But B is a little bit tougher, so let's look at B. If we can find the relationship between A and B, that'll tell us what B is. So working backward, we can see that A crosses the x-axis where B has a horizontal tangent. That means A must be the derivative of B. Right? And you can see it clearly here, right? That's how we did our problem earlier, right? Horizontal tangent at B crosses the x-axis for A. That means A is the derivative of B. So that means B is S double prime. And you just keep going like that, and you set up a chain of reasoning. B crosses the x-axis where C has a horizontal tangent, right? Here's where B crosses the x-axis, and here's where C has a horizontal tangent. So B is the derivative of C, and then there's only one curve left over. A is the derivative of B, B is the derivative of C. That means C has to be the derivative of D, and that tells us our order. So S is D, S prime is C, S double prime is B, and S triple prime is A. So just looking for vertical tangents will help you a lot. Eventually, we're going to learn how to just use pictures. That comes in chapter 3. We're going to be able to look at just the graph of B and learn about D, right? All right. And we'll revisit this picture later. All right, so that's the end of the instruction. So if you need extra practice, there's a lot of good study sets here. All of these problems that I put up here are really, really good. Of course, you have the online free resources that are great. So I really don't have anything else to say about that. But as promised, we have the proof of the theorem as our last slide. I just want you to make sure that you can understand this proof. Okay, so remember, this is the only theorem in the section, theorem 2.2.4. If a function is differentiable, it's continuous. That's what we're trying to show. Okay, so to show that f is continuous at a, we have to show that f of x minus f of a as x approaches a goes to 0, right? So that's basically just the numerator. This is the numerator of this expression. It's our MPQ function again, right? Remember, f of a, that's the function at the point, and f of x, that's the moving function as q gets closer to p. So all we have to do is show that the y-coordinates of these two goes to 0. Okay, so continuity just shows that the limit as x goes to a, remember, these are y-coordinates. So we know f is differentiable, so the derivative exists at the point. And this is the definition of the derivative that we saw earlier, right? This is the definition of a derivative at a point. We saw this in section 2.1. What we do here then is we just rewrite an expression, okay? So what we're basically doing is we're just setting up a true statement, okay? F of x minus f of a is this times that, because we could cancel this. So we're just setting up a true statement, and we're going to do different things to both sides. That's all we're doing here. Right? So this is our MPQ function. So you multiply this by x minus a, this cancels, and you get that. So what we do now is we take the limit of both sides. Okay? So we tack a limit on here, and we tack a limit on here. This is exactly our derivative. Right? Right? This part here. So we distribute the limits, right? Using a limit law, we're allowed to do that. Replace this with our derivative, which is this. And then this, we know goes to 0, right? We have a limit law for this too, right? The limit of x minus a as x approaches a, right? The limit law says we can just replace x with a because this is continuous, right? We just have to show, right, because these are x coordinates, we have to show that this goes to 0. So this expression is the same as this expression. So f prime of a is just a number times 0 is 0. So we've proven the theorem. Okay, so again, we know that the x coordinates approach each other the way the number line works. So it's like an epsilon delta proof, right? We have to show that the y coordinates can also be that the limit of the y-coordinates can go to 0. All right, so that's it for today's lesson. This is the last information that's going to be on the exam. Sometime in this next coming week, the week before the exam, I'll be posting lots of review material, practice problems, and things like that on Canvas. As usual, if you have any questions, let me know, or post a question in the discussion forum. And I will see you guys next video. Bye-bye now.